Hello and welcome. In this video, we are going to determine the adiabatic flame temperature, the exit temperature in this case of methane mixed with a 50-50 mixture of oxygen and nitrogen, and the chamber is adiabatic, no heat transfer, therefore the exit temperature is the adiabatic flame temperature. The theoretical amount means that if the reaction were theoretical, which means complete and no excess air or fuel, in that case the amount of oxidizer required is called the theoretical amount. Anyways, so we'll seek the adiabatic flame temperature for three different situations. Complete combustion, that is C going to CO2, H going to H2O, with NPG model where Cp and Cv are held constant. Complete combustion with the IG model, and IG model assumes Cp is a function of temperature, and then in complete combustion, that is, we are going to allow any kind of product such as CO, nitrogen, H, OH, you name it, but we will find the product's composition using chemical equilibrium. So let's go and get started on this ambitious problem. Go to the test steps page and we follow open specific branch and the premixed combustion. Let's first start with the PG mixture model. So let's set up the reaction. Methane is our fuel, and let's compose our oxidizer. It's a 50-50 mixture of, one is by default oxygen and nitrogen, but this is not, we still don't know exactly what the oxygen, this is not the amount of oxygen and nitrogen we want, this is the proportion. Now let's go and set up the amount by going to theoretical combustion with user-defined oxidizer. It's best to user-defined oxidizer with known excess deficient amount. In other words, later on to do a parametric study, we can change lambda. So lambda equals 100 means theoretical amount. So for the parametric study, we can use 110 mean 10% excess oxidizer. So this, when I execute this action, that means the reaction is now totally poised for methane reacting with theoretical amount of a 50-50 oxygen-nitrogen mixture. So the reaction is totally balanced. So now is the time to figure out the states. The reactants state is 100 kPa and 298 Kelvin. And the amount of fuel is picked up right here. Not fuel, an amount of reactant is picked up from the reaction itself. For the products, we have 100 kPa, but the temperature is unknown. So we go to the device panel and set up the reaction, set up the combustion chamber. State 1 and 2 are our inlet and exit. There is no heat transfer, there is no work transfer. Once we calculate, you will notice in the state panel, J has been pasted back. All we do is to calculate here, and a temperature of 5243. Let me write it down. A very high temperature is found as the adiabatic flame temperature for 50-50 mixture of oxygen and nitrogen burning with methane. Well, now that we have found the solution for the NPG model, we'll go and launch the IG model, and going back to the test steps, combustion and chemical equilibrium, and we are on a premixed NIG mixture model. Again, we are going to do exactly the same thing. Methane, select methane. Now let's select the oxidizers. Use a defined amount, 100%, and that balances the reaction, the same reaction that we did for the PG model. So every step is exactly identical here, except the model used is different, so therefore the answer should be different. So for the products, we have 100 kPa. We don't know what is the temperature. We go to the device panel, and it's premixed reaction. The reactants and products are selected. as state 1, 2, no external work or heat transfer. That substitutes J into the state panel, and the temperature is found to be 3838 Kelvin. So look, when the Cp was assumed constant, the temperature was considerably higher. The temperature was found to be 5243. You can go back, you can take a look, compare this temperature with temperature of the PG model that we found. That was the state panel 5243 as opposed to 3838. So let's now go and solve the problem using the chemical equilibrium model. So let's start that here. Go back to the same page, but this time an IgE mixture model. Once again, we are going to set up the reaction, at least the reactants, the same way. Methane is added, and then for the oxidizer, we set it up. But again, equilibrium combustion with the known excess deficient user-defined oxidizer, 100%. So this time, when I click execute, notice only the reactants are found, products are unknown. We have to set up the products because that's the thing about incomplete combustion. We don't know what are in the products. So let's select the typical products, add those. So what happens is that now we have chosen what products we want to see in the equilibrium analysis, but their amounts will be determined along with the final temperature through equilibrium calculations. For the state panel, for the inlet, we know everything, which is the reactants, 298 Kelvin. And for the exit, we only know the pressure. Go back to the device panel. So rest of the process remains similar. No heat transfer, no work transfer. We calculate, come back to the state panel, and run another calculate. The second calculate, this time it will do the equilibrium calculation, and the temperature is found to be 2808. It's considerably lower. Notice 2808 is almost 1000 Kelvin lower, and this is the most realistic temperature for methane combustion with 50-50 oxygen and nitrogen in theoretical amount. So how do you go about if there were 10% excess oxygen? Okay, let's go back to this model. Let me just show you in one place. This is the temperature we found with the IG model. This is the app for an IG model, that is Cp is considered variable. However, we chose the complete reaction path, so that's why you will see the product of combustions are, if you go back to the reaction panel, you can see the reaction. We have only H2O, CO2, and nitrogen in the products. So it's a theoretical reaction. It's a complete reaction with theoretical amount of air. Okay, so now to do excess air, we can just go back to balance the reaction with user defined, and if you want 10% excess air, excess oxidizer, we just put 110 here and execute. This time the reaction will have some leftover oxygen as we expect. It's still a 50-50 mixture of oxygen and nitrogen. Instead of 2 and 2, we have 2.2 and 2.2, a 10% excess oxidizer. These panels can be updated by clicking the super calculate button, and we can go back to the state panel, and the temperature now found is 3623 as opposed to 38. So when we used excess air, you can see that the temperature, not air, excess oxidizer, the temperature has gone down. Exactly the same way we can go and exactly the same way we can go and, so let me write down this number. So the new temperature is 3623 Kelvin when we have 10% excess air. How do we solve that problem? Using the equilibrium model? Well, if we, I'd say this is a complicated problem. We start from scratch again, super initialize, methane is added, and then we compose the oxidizer, compose the reactants by using lambda of 1.1 or 110%. As you can see, the reactions are all set up here, and the products, we are going to go and select typical products, add. You can play with that. You can selectively eliminate a few to see which of them are important in determining the adiabatic flame temperature for a particular reaction. Okay, so now that we have set up the reaction right here, to find the amounts, we'll go to the state panel. Pressure is known, temperature is known. For the reactants, for the products, we only know pressure, doesn't change. We go to the reactants device panel so that we can solve the energy equation there. No heat transfer, no work transfer. Well, this calculate does post invisible properties into the state panel. We can see the mass coming here. But now when you click a calculate button, again the server will compute the product composition and then find the temperature. Based on that, enthalpy will be calculated, and based on that, temperature is calculated. 2783. As you can see, 2783 is smaller than what we got before. 2808 was the temperature we obtained when we use the equilibrium calculation for 10%. So as you can see, the temperature has dropped by almost 100 Kelvin. That's not so much. I would say about 25 Kelvin or so. So for the equilibrium calculation, it seems like the temperature drop is not as drastic as in the complete combustion using IG model. So I'll stop here, and I hope you get the idea of how to use the combustion and equilibrium apps.